Assalamu alaikum everyone. This is lecture 6 on nonlinear control system. We are discussing chapter 2, phase plane analysis. Basically, in the last few weeks, we have followed the book Applied Nonlinear Control. So one of the topic from the nonlinear control system by Khalil was actually uh, attracting my attention. So I was hoping that this will help us to understand some of the fundamental thing about the nonlinear control system. So that is why I'm just covering that one. And this is actually article uh, 2.3, article 2.3, that is qualitative behavior near equilibrium point. So somehow we already have discussed that how to obtain the equilibrium point, or basically the points where the system state always wants to stay there. So once it is there, always stays there. So basically the derivative terms those vanished. So that is why they are called equilibrium point. Now, in general, the quality behavior of a nonlinear system near an equilibrium point can be determined via linearization with respect to that point. Okay, so say uh, we have a system x1, f1, function of x1 and x2, and x2 dot equal to function of another function of x1 and x2. So this is our system, and we want to know the qualitative behavior near an equilibrium point. So let's assume that P is our equilibrium point, that is P1, and P2 is our equilibrium point. So what we have to do is basically we have to linearize this one about this point, and most often the linearization around that equilibrium point gives a fair idea of the behavior of the nonlinear system around that point. Okay, so let's look at the process that this book says you should follow. Is basically expanding this equation in Taylor series. Okay, so expanding this one, say we are getting this x1 dot equal to function of p1, p2. There is actually initial value. Then we have a1, 1, x minus p1 plus a1 to x minus p2. Then we have h, o, t, that is higher order terms, because we are interested about linearizing the thing. So we are ignoring those higher order terms. And x2 dot is function of p1 and p2 around that point. Then a21 function of x minus p1. Okay, so actually it will be x1 and this will be x2. Okay, then plus a22 x2 minus p2 plus again the higher order terms of the second equation. So this is and what is actually our a11. A11 is partial derivative of the function f1 with respect to x1, and a12 is partial derivative of the same function f1 with respect to x2. Similarly, a21 is basically partial derivative of function f2 with respect to x1. A22 is partial derivative of function f2 with respect to x2. Okay, so and also we have to be careful about the thing that all this partial derivative actually has to be with respect to that point P. So we have to be careful about that here the point is P. In all the cases, we are referring to that particular point P because we are interested about the magnitude at that point. Okay, so now also you can write in this way that instead of writing P, you can also write the point. So you can also write something like this: x, which is x1 and x2, equal to P, which is P1 and P2. Okay, so now from this equation, since these are equivalent point P1 and P2, so basically this value and this value has to be equal to 0. Okay, so should not be this is a root, isn't it? So P(f1), P1, 2, and f2, P1, 2 has to be equal to 0. And also we are not interested about the higher order term because we are doing the linearization. So what is left is this parameter, this parameter, this parameter, this parameter. This vanishes because of their magnitude is 0. And also we can simplify our equation by one assumption that we can assume that x1 minus p1 can be assumed as y1 and y2 equal to x2 minus p2. So if you assume that and you replace this one, actually if you differentiate this one, that what you get, y1 prime is x1 prime because p1 is constant. Y2 prime is actually x2 prime. So now if you replace this and this into that equation 1, 2, then what we are going to get is basically y1 dot equal to x1 dot equal to basically a11 y1 plus a12 y2. I already had excluded the higher order terms, so then y2 dot equal to x2 dot equal to a21 y1 plus a22 y2. Okay, so now from this equation, what we can write? We can rewrite this equation as y dot equal to a y. Okay, so what is a? A is basically our system matrix, or in terms of the equation, this is a11, a12, a21, a22. Or partial derivative form, you can also write df1 by dx1, df1 by dx2, del x2, and then del f2 by del x1, and del f2 by del x2. And also you can always, you have to remember that this is basically for a particular point x equal to p. Now, what is the del f by del x? So this del f by del x, this matrix is actually known as, this matrix is known as Jacobian matrix. Okay, so and once you place the value with respect to any particular equilibrium point, then we call it the A. So basically A is del F by del X subjected to any point that is X equal to P. Okay, so once you evaluate the Jacobian matrix, then actually we get the matrix A. So this the system matrix is actually helps us to find out what is happening in our system. And also from this one, from the system matrix A, we can actually obtain the eigenvalues of the system. So once we know the eigenvalues of the system, we can always find out what will be the equivalent behavior of the system. So what about the roots? So I think this portion is already done in one of the previous class, that how to find out the eigenvalues and how to figure out whether it is a focus or focal point or a stable node or unstable node, stable focal or unstable focal or center. Okay, so all this thing is already been figured out. So just the theory was not discussed from where that A was coming. So this is the relevant theory related to that one. Now, as we already said, that near the equilibrium point, if the system's behavior is uh, very close to the linear version of it. So we have a nonlinear system and we have an equilibrium point. So near the equilibrium point, if we linearize the equation, and that behavior of the linearized equation will almost predict whatever the nature of the behavior in the nonlinear system. So if it is in the linear version, it is a stable node, then in the nonlinear also they will behave similarly. So this is what we already have seen, and based on this approximation, we have already figured out few examples of nonlinear system in the last class, in one of the last class. But the question here is whether it is always true or not. So whatever the approximation we make by linearization, whether that gives us always the correct information about the system's behavior or not. So that is the question. So let us answer this question with respect by solving one problem. So basically, this is also from Khalil's book. This is example 2.5. System is given, and this is x1 dot equal to minus x2 minus mu x1 square plus x2 square, and x2 dot equal to x1 minus mu x1 square plus x2 square. Okay, the system is given. So let's apply the eigenvalue theory, values. Let's figure out the eigenvalues and predict the system behavior around the equilibrium point. So one of the equilibrium point of this one, the equilibrium point for this one, if you solve it, is going to be 0, 0. So I'm not solving that one, rather leaving it for you. But our equilibrium point P is basically 0, 0. So now what we have to do is we have to find out the Jacobian matrix first. So basically d del f by del x we have to figure out, and that is nothing but del f1 by del x1, del f1 by del x2, then del f2 by del f2 with respect to del x1, and del f2 with respect to del x1, and then after solving it we have to replace the point here. So that will give us actually the magnitude of the matrix A. So now if you differentiate the first function with respect to x, so this is constant, only the second term you have to derive it. So what you will be getting is if you multiply and then derive it, it is basically minus mu x cube. So 3x square will be coming. So minus mu minus 3 mu x square, you can say x1 square. And the second one is x2 square is actually constant, so you can say minus mu x2 square minus mu x2 square. Okay, so and then again if we differentiate the first function with respect to x2, then we have minus 1, and x2 if we differentiate, then it will be 2x2. So basically minus 2 mu x1 x2. Okay, so again second one, if you differentiate then with respect to x, then it will be 1 minus 2 mu x1 x2, and the second one will be basically minus mu x1 square and minus 2 3, because x2 cube, so 3 mu x1. Okay, so 3 mu x2 square. Okay, so then you have to place your point, that is x equal to 0 0. And if you place that one, so you can see this whole parameter will be becoming 0, this one becoming 0, this one becoming 0, this one is also becoming 0. So what will be left is 0 minus 1 1 0. So from this one we have to find out the eigenvalue, that is lambda I minus a, the determinant of that. So that will give us lambda 1 minus 1 lambda. So now lambda square plus 1. So basically lambda 1 2 will be plus minus j. So we see that imaginary portion is only available in the roots. So we can assume that imaginary means oscillation. Oscillation means actually center or circle or elliptical, but there should be pure oscillation and a series of oscillation, to be honest, like for different magnitude from different location. If you start, it will give you different oscillation like this. Okay, so a series of oscillations. Okay, so this is the prediction based on the linearization around the equilibrium point. But what is the actual scenario? What will be the actual behavior? Okay, so this is what we want to see. And because of the imaginary nature, it is actually marginally stable, as we already know, that it will be never decaying or never exponentially increasing. So from the same equation, so and the way to figure out is what is actually happening is convert this one into the polar form. So basically we are assuming that x1 equal to r cos theta and x2 equal to r sin theta. Basically r square equal to x1 square plus x2 square. And also you can find out the angle. Okay, so the angle can also be figured out. So tan theta is basically tan theta is basically x2 by x1. Okay, now differentiate this one first. Differentiate this one. What we have is basically twice r dot equal to twice x1 x dot plus twice x2 x dot x2 dot. So 2 can be cancelled out. So what we are left with is r dot equal to x1 dot plus x2 dot, and x1 x2 values are available here. So let us just replace the value of x1 and x2. So x1 times minus x2 minus mu x1 square plus x2 square. Okay, so this is the first one, then plus x2 x1 minus mu x2 x1 square plus x2 square. Okay, so let us try to simplify this one a bit, and also you can we know that x1 square plus x2 square is nothing but r square. So r dot equal to minus x1 x2 minus mu x1 square. Then you can write r square. Then we have plus x1 x2 minus mu x2 square r square. So this one is getting cancelled out. What is left is r dot equal to mu r1 can be taken common off. So mu minus mu r square. So x1 square plus x2 square. So basically minus mu r square into r square. So minus mu r cube. And also in the other side we have 1r. So 1r can be, 1r to the power 4. So 1r can be actually cancelled. So what is left is r dot equal to minus mu r cube. Okay, so this equation is enough for us to actually figure out what is happening. It's still, you can also go for what is the value of the theta dot. You can also find out the value of the theta dot, but I'm not doing it because in some other example I'll be doing it. So here, as you can see, what you can find is r dot is always a negative value. R dot is always a negative value that is lesser than 0 as long as mu is greater than 0. That means as long as mu is positive, r dot is always negative. So basically, once this is the scenario, it is actually the trajectory near the one will be actually resembling a stable focus. Okay, so always going to the equilibrium point. Okay, so something like this, always will have a trajectory, something like we will be going to the equilibrium point, something like this. Okay, r dot is always reducing. But if the mu value is negative, in that case, r dot is becoming positive, and in that case, you will have an unstable focal, that is, you will have something like this. Okay, so now what we predicted using the linearization is a marginally stable scenario, and what is the reality is far beyond that imaginary case. So we can always approximate, but it may not always give us the correct value. So we actually have to be careful about it. So near the equilibrium point, it may behave temporarily like a oscillatory nature, but in real life, this is actually a stable or unstable focal based on the values of the mu, whether they're positive or negative. So this is one of the critical issue that we should address in this scenario, because of the fact that we cannot always be happy that we have a specific solution and this is what is true, but it can always change because of the nonlinear nature, because sometimes whatever the linearization may not give us the correct uh, result. Okay, so this is about our qualitative behavior. Some other example is there, so if you are interested, you can always cover those and go through those in the playbooks. Now, next is what we want to discuss is basically the limit cycle. So, what is a limit cycle? Limit cycle is basically something that is having an uh, isolated closed curve. That is what is called a limit cycle. In the Van der Pol equation, we have seen some limit cycle. So from the phase plane analysis, a limit cycle is defined as an isolated closed curve. And this is, I think, article. This is one. Now we actually going back to the slotting book again. So limit cycle. Limit cycle. In phase plane's perspective, it has been defined as isolated. Defined as isolated closed curves. Okay, so the trajectory has to be both closed, which actually means that it has to be periodic in nature. So that is why it is called closed. And also it has to be indicating that a limiting nature. That means there should not be any other nearby trajectory, like the one previously, the last example we have seen that a series of curves. So they are not isolated. This is also one of the examples that mass spring system that we have discussed, mass spring system, or in one of the satellite system, you have some electrical closed curves, something like this. So these are not isolated. So since they are not isolated, they cannot be called as a limit cycle. Rather, in the Van der Pol equation, there is a single isolated case where actually we have one curve that is, and some of the curve is tending towards it, and some of the trajectories are tending towards that one, and some may actually go away from that one. So depending on the nature, depending on the motion patterns of the trajectory in the vicinity of the limit cycle, they are actually classified in three kinds of limit cycles. So based on motion pattern. Okay, so there is three kinds of limit cycle. Okay, so they are called, the first one is called stable limit cycle. Okay, so as time goes to infinity, all the trajectory in the vicinity of the limit cycle converges to it. Converges to it. So graphically, what it means is basically, if you have a limit cycle, we are assuming that not necessarily always has to be circular, but we can assume that this is a circular limit cycle we have. This is the limit cycle. And once you are outside that limit cycle, somewhere outside, so you will gradually converge it to the limit cycle. It will continue there. And if you're inside as well, so you will have similar nature. So somewhere if you start, you will be always starting to the limit cycle. You'll be always ending to the limit cycle, somewhere, something like this. So always in the limit cycle. So outside it is converging and inside it is diverging, so that it end up in being in the limit cycle. So this is stable nature. From both sides it is actually coming towards the limit cycle. The second one is actually unstable limit cycle. So in the unstable limit cycle, I think you already predicted what is going to happen. That is, as time goes to infinity, it will be diverging. So all trajectories will diverge from the limit cycle. Okay, so if you try to draw it graphically, if you try to represent it, then we are going to see something like this. So from the limit cycle, say it will be starting from somewhere here, then it will be going towards the center. So this is one, and this is our limit cycle. Actually, it would have been better if we could have drawn it with different colors. So it will be going towards also diverging, something like this. Okay, so this is as time approaches infinity, it is always diverging, both innerwards and outerwards. And there is another one that is called semi-stable limit cycle. The third one. Okay, so in one end it will be diverging, and one end it will be converging. Okay, so as t goes to infinity, some of the trajectories, some of the will converge, and some of the trajectories will diverge. Okay, so let's try to represent the graphical way. So this is our limit cycle. So outerwards, from the outerwards, it will be always, sorry about it. So outerwards, it will be always converging. Outer periphery, it is always converging. Okay, so this is the one. And from the innerwards, it will be diverging towards the origin. Okay, so in some way it is stable. From the outside, it is going to the limit cycle, and from the inside, it is actually diverging. But from the stability point of view, it is not going in towards the infinity. So going inside, and if you have some equilibrium point inside, and it's going to the equilibrium point, is also not a bad idea. So that is why in some cases it is converging, in some cases it is diverging. That is why it's called semi-stable limit cycle. Now, whether our limit cycles are actually existence of the limit cycle, how can we find those? One example from your slot-in book, that is example 2.7. Example 2.7, three part is there. So yes, all three will be using same idea, and actually the example of your 2.5 of the Khalil book. So similar idea will be applied here. So x1 dot equal to x2 minus x1 square plus x2 square minus 1, and x2 dot equal to minus x1 minus x2 x1 square plus x2 square minus 1. So this is our system, and we have to predict whether it has limit cycle, stable limit cycle or not. Now, whether there is a limit cycle, this is question number one. And if there is a limit cycle, whether it is stable, unstable, or marginally stable. Okay, so same thing we have to do. R square equal to x1 square plus x2 square. So basically, as we have done in the last one, so r dot should be equal to x1 dot plus x2 dot. Now you replace the value of x1 dot and x2 dot. So x1 x2 minus x1 x1 plus x2 square can be written as r square, so r square minus 1, then minus plus x2, then minus x1 minus x2, again r square minus 1. So what we have here is basically x1 x2 minus x1 square r square minus 1, then we have minus x1 x2 minus x2 square r square minus 1. So this one and this one getting cancelled out. What is left is you can take common of r square minus r square minus 1. So whatever left is x1 square plus x2 square. On the other side we have r dot. So x1 square plus x2 square is nothing but r square. So what we have is minus r square minus 1 r dot. So basically 1 r getting cancelled out. So r dot is becoming minus r square minus 1. Now, actually, what we know, once a trajectory is on the limit cycle, what we know is that will always try to remain in the limit cycle. Okay, so this is a trajectory. So whether there is a limit cycle or not, the first thing is for the limit cycle, r dot should be equal to 0. So that is possible, r dot equal to 0 only if r equal to 1. Okay, so if the radius is 1, then as you can see, the right side is becoming 0. So we can say that yes, there is a limit cycle for this particular system for the values of r equal to 1. So this is the first thing to answer. And the second question is whether your limit cycle is stable or it is unstable or it is marginally stable. So to answer that one, we can apply few other conditions, like what will be the value, what will be the value of r dot if r equal to greater than 1. If r equal to greater than 1, that means you are outside the circle. So the circle with radius 1. So this is your radius 1. So now we want to know if somewhere here we are, then whether our trajectory will be converging or diverging. Okay, so if r equal to greater than 1, so if r is 1, then this term is positive, and if this term is positive, then this will be remaining negative sign. So r dot will be becoming lesser than 0, negative. So that means it will be having a negative or decaying nature. So it will be converging to the limit cycle. Okay, so from the outside, it is actually converging. Okay, so converging. Now from the inside, what will happen? So just take any point inside that is R is smaller than 1. So if R is smaller than this quantity is becoming negative. So this is negative. So negative, negative. The R dot will be actually now greater than 0 or positive. So if it is positive, so your trajectory will be actually again will increase and eventually will be converging to the limit cycle. Okay, so increasing nature. So basically it will be diverging from the inside, diverging. Bottom line is both the trajectory, whether it is inside or outside, it will be converging to the limit cycle. So this is a condition for our stable limit cycle. So you can conclude that our limit cycle will have a limit cycle, and limit cycle is a stable one. As I said, the theta dot is not that important, but it is always better to know how to find out the theta dot as well. Okay, so as we said that x1 equal to basically r cos theta, and x2 equal to r sin theta. So tan theta is basically x2 by x1. So theta equal to tan inverse x2 by x1. So if we apply the derivative of with the tan inverse, then what we have is theta dot equal to 1 by 1 plus x2 by x1 whole square. Then also you have to find the derivative of this one. So basically d by dt of x2 x1 series of derivatives. So finally what we are going to get is if we simplify x1 square plus x2 square, and if you take a derivative of that one, then it will be x1 x2 dot minus x2 x1 dot divided by x1 square. So x1 x1 getting cancelled out. What is left is x1 x2 dot minus x2 x1 dot divided by x1 square plus x2 square. And now you just have to apply, you just have to replace the value of x1 and x2 dot. And once you do that, and you do a bit of simplification, then you are going to get, we have minus x1 square plus x2 square by x1 square plus x2 square. So eventually they are getting cancelled out. So it is just constant value. And it has hardly any effect on determining the limit cycle or the nature of it, whether it is uh, stable or unstable. Okay, so this is how to deal with the limit cycle. So as the similar polar form transformation we have seen for the equilibrium point behavior near the equilibrium point as well. So it can apply for both the scenario. Okay, so once, so there's two other examples. So you do it by yourself. I think 2.7b and c. So do it by yourself and verify whether the limit cycle is stable, unstable, or marginally stable. So next thing that we should know or try to find is what is the condition or criterion for existence of the limit cycle. This is article 2.6 from the Slotin book. There is three commonly used formula basically. One of them is mainly used, and the other two at times they're also used. So, example, this is article 2.6. Existence of limit cycles. Okay, so there is three theorems. So the first theorem, it is related to the number of the singular point or equilibrium point with respect to the number of the saddle points. So say if number n is equal to your number of singular points, number of singular points, and s equal to number of saddle point. Okay, so always there will be relation maintained between n and s is n equal to s plus 1. So how many saddle points you have? If you want to have a limit cycle, then n should be, the equilibrium point should be at least one more than your saddle point. So this relation will be followed if the limit cycle exists in the second order autonomous system. So this is the theorem, and this theorem is known as, they have used theorem 2.1, and the inventor's name is Poincaré. Okay, so Poincaré's theorem, or sometimes it is also known as index theorem. Index theorem. So derivation is a bit mathematically involved, so the author actually escaped that one. The intuition is relatively easier. So the simplest intuition is a limit cycle must enclose at least one equilibrium point. So a limit cycle must enclose one equilibrium point. Okay, so if your saddle point is 0, so n should be equal to 1. So your limit cycle at least should enclose one equilibrium point. In the other way, what you can say that if you're given some trajectory and that doesn't encircle or enclose any equilibrium point, we can say that there is no limit cycle. Okay, so this theorem is basically used for nullifying the existence of the limit cycle. So basically, if some region is provided to you, say we are giving a region, any arbitrary region, this region, and we want to know whether there is a limit cycle or not. So if we can prove that there is no equilibrium point inside this region, then there should not be any limit cycle, because limit cycle should be enclosing at least one equilibrium point. So if there is one equilibrium point, then we can, there is a possibility of having the limit cycle inside. But it is not always rigid. So that is why it is mainly used for nullifying the idea. So basically, if any region that doesn't have an equilibrium point inside, that means there is no limit cycle inside. Okay, so this is your first theorem. Derivation is complicated, so the author actually left it. Rather, we have to use the intuition behind the theorem. The next one is slightly more important, sorry, the most important among the three basically. So this one says that this is theorem 2.2. Theorem 2.2, that is Poincaré-Bendixson theorem. Okay, so they invented it. What is it says is, if a trajectory of a second order autonomous system, if a trajectory of the second order autonomous system remains in a finite region omega, so second order trajectory of a second order finite system is within the region, say omega. Omega is a region. Theorem 2.2, Poincaré-Bendixson theorem. So the theorem says if a trajectory of a second order autonomous system remains in a finite region omega or R, in some books they prefer as R, in some finite region R or omega, then one of the following is true. So we have a trajectory in a region R, or omega is the region. And if there is a trajectory inside that one, confined in that region, then one of the three is true. Number one is the trajectory goes through an equilibrium point. Okay, so the trajectory goes to an equilibrium point. This is the first one. Otherwise, the trajectory tends to an asymptotically stable limit cycle. The trajectory tends to an asymptotically stable limit cycle. Or finally, third is the trajectory is itself a limit cycle. Okay, so three, if any trajectory is within a region omega or R, which is a finite region, it is confined there, then one of the three is true. The trajectory, either it goes to an equilibrium point or the trajectory tends to a asymptotically stable limit cycle, or trajectory is itself the limit cycle. So one of the three is basically true if uh, you have a trajectory inside any confined or defined region, finite region. So this is, I think, one of the important one in case of finding the existence of the uh, limit cycle. And intuition is very simple. So derivation is slightly complicated at times, but intuition is very, very simple. Intuition says that if you, in your space, you have a region, so this is maybe your omega or region R, whatever. In that region, if you have any trajectory, so what the trajectory will happen. So one of the first thing happen to the trajectory is there is a equilibrium point, and our trajectory is going to the equilibrium point. So this is one case. The second case is in our system there is a limit cycle. So our trajectory after some time will be actually converging with our limit cycle. So this is the second possibility. Or if your trajectory itself is a limit cycle, so it will follow a path like this. So this is a three case. There is no other case. So it has to be a decaying nature. So if it has a decaying nature, it will go to the equilibrium point. If it is having no decaying nature, and if you have a limit cycle, then it will decay to the limit cycle. And the third one is your the limit cycle itself, so it will always be there. So this is the intuition behind this theorem. Now, in slotting book, there is no further things have been provided, but a version of this theorem, which is slightly modified, is been discussed in Khalil's book with a bit of more mathematics being involved. So what they are saying is actually this is called lemma 2.1. Lemma 2.1 from the Khalil's book. What it says is that again the idea is same. Say M is the region, they're calling it M. M is the closed boundary. Closed boundary. Closed bounded subset they're actually calling. So we'll also keep it to that. And their theorem says that M contains no equilibrium point or contains one equilibrium point such that the Jacobian, it is del phi, del f by del x is at this point as eigenvalue, that is positive real number. Del f by del x has eigenvalue with positive real eigenvalue. Okay, so this is what is they are saying. So each trajectory starting M stays in M. So this is one thing they are saying, and the other one they are saying is each trajectory starting in M stays in M. Okay, so this one is slightly more involved and mathematically involved, and I found it quite good as well. So first thing is M is a bounded surface, and M contains no equilibrium point, or it contains one equilibrium point, and the Jacobian at that particular point is basically having eigenvalue that is positive, you have positive real part. So if you have positive real part, it has to be unstable focus or unstable node, and every trajectory starting at M stays in M for all future time, and if all these are true, then M contains a periodic orbit. Okay, so if these are true, this is true, then M contains a periodic orbit. Okay, so this is a different version, and also another version is available, I think, from one of the MIT slides, but let us keep it with this one. So how to investigate the behavior of the trajectory that is trapped inside M? So to discuss the behavior, the tool that you can use is, say that consider a closed curve defined by Vx. Vx equal to C is a closed curve where Vx is a continuously differentiable. Okay, so analytic. and the vector field f x, we assume that the vector field is fx at point x on the curve points. Okay, so we have a closed curve and that is defined by Vx equal to C, and we have a vector field on the points on the curve is Fx. And now what we should have is on the curve of the point, it should have, say this is our curve, Vx equal to C, and the vector field at that curve, if it is inwards, then actually you're confined in that zone. If the vector field is outwards, then actually you're diverging. Okay, so this is the scenario. So to how to find out whether the curve is inwards or outwards, for that one, we actually have to find out the inner product of the fx and the divergence, the gradient of v. So basically fx dot a gradient of which is nabla vx. So if you can find this one, and if the value of this one is smaller than 0, that is we are inside, and if fx dot nabla vx is greater than 0, that is we are actually diverging from that curve, points on the curve. And if fx dot, and this dot product dot nabla vx is basically equal to 0, that means we are neither diverging or converging. We are actually always on the surface. Okay. So let us apply the condition of Vx fx dot nabla Vx equal to nabla Vx is nothing but partial derivative of v with respect to x. Then f1 has to have x component and x2 component. So that will be going to a inner product, or basically dot product. Okay, then plus partial derivative with respect to the second parameter, that is del x2 with f of component of f with x2. Okay, so now this is the case, and if this value is lesser than 0, that is we are converging inside the surface. If this value is greater than 0, then actually diverging from the surface. So we actually have to apply this condition and to figure out what is happening. So whether we have any limit cycle or not. Okay, so let us apply this one on one of the example from your chapter, from your Khalil's book. So first of all, let's what the question says. The question says we have a system, and the systems, this is example 2.8. X1 dot equal to x1 plus x2 minus x1 square plus x2 square, and then x2 dot equal to minus 2x1 plus x2 minus x2, x1 square plus x2 square. So this is the system. Now let us try to apply this condition to check about the system. So the equilibrium point of this one is again 0, 0. Most of the cases it is 0, 0. So, and then we can also find out the corresponding values. Okay, so we know how to find out the equilibrium point, isn't it? So next thing is finding the Jacobian matrix at 0, point, that is del f by del x at x equal to 0. That will be basically del f1 by del x1, del f1 by del x2, then del f2 by del x1, del f2 by del x2, and then you have to set the point x equal to 0. So now if you apply this thing on that equation, then we can find out that is becoming 1 minus 3x1 square minus x2 square, 1 minus 2x1 x2 minus 2 minus 2x1 x2, and 1 minus x1 square minus 3 x2 square. So your x has to be equal to 0. That means x1 x2 both is 0. So what we'll be left with is 1 1 minus 2 1. Okay, so this is our a basically. So now determinant of this one, so lambda I minus a. I'm just skipping a few lines. I hope you'll be able to do it. And that is basically determinant of lambda minus 1 to lambda minus 1. So what we have is lambda minus 1 whole square plus 2. So simplification, lambda square minus 2 lambda plus 3. So if you apply now lambda 1 2 quadratic solution, that is minus b plus minus b square minus 4 into a into c divided by twice a. So basically plus 2 plus minus root over minus 8 by 2. So 4 can be taken away. So minus, so basically 1 plus minus j root over 2. So as you can see here, we have a positive real part according to the theorem. And let's define m equal to say a zone which is Vx and which is lesser or equal to C, defined by a surface. Okay, so say that Vx equal to nothing but a circle, that is x1 square plus x2 square, and we are assuming that C is greater than 0. So on the surface, actually Vx equal to C. So we are trying to find out on the surface what is our direction. So on the surface, if you apply the direction, that formula that we have derived, del V by del x1 f1 plus del V by del x2 f2 equal to, so twice x1 and f corresponding to x1, the first function that we have to bring it here again, x1 plus x2 minus x1 square plus x2 whole square. Then plus derivative of that one is actually 2x2. Then bring that function f2 minus 2x1 plus x2 minus x2 x1 square plus x2 square. Okay, so if you simplify a bit, then what we are going to get is 2 x1 square plus x2 square minus 2x1 x2 minus 2 x1 square plus x2 square whole square. So this is a simplification. Okay, so what we get here is that it has to be, this one has to be lesser than 0, so that it is trapped inside that surface. So how can we prove that this quantity is actually lesser than 0. So what you can say that del v by del x1 f1 plus del v by del x2 f2, this parameter is actually creating trouble. Somehow if we can replace this one by some parameters, say x1 and x2 can be replaced by x1 and x2 can be replaced by some parameter called okay, so if we can find out that x1 square plus x2 square. So always we can see that this parameter x1 square plus x2 square will always be greater than twice x1 plus x2. Okay, so this parameter will be always greater. So if we can replace 2x1 by x2 by this parameter here, so this side will be always greater than the other side. So we can say that this will be always greater than this one. So 2x1 square plus x2 square minus x1 square plus x2 square, sorry, 2 whole square, then we have plus x1 square plus x2 square. So this one can be slightly simplified, and what we'll have is cancelling each other. So what we'll have is 3 3 they'll be added together, so there'll be 3x1 square plus x2 square minus 2x1 square plus x2 square. So basically what we'll have is 3c minus 2c square, and we proved that basically del v by del x1 f1 plus del v by del x2 f2 is lesser or equal to 0. So what is mean is that we do have we can conclude that there is a limit cycle inside the surface M. Okay, so this is your lemma 2 according to the Khalil's book. Okay, so the last one is last theorem that we have is known as Bendixson theorem. So the Bendixson theorem says, theorem 2.3, so it says that for a nonlinear system, no limit cycle exists in the region omega of the phase plane in which that del f1 by del x1 plus del f2 by del x2 doesn't become 0. Okay, so if this one doesn't vanish or say change sign, in that case it is not possible to have any limit cycle. Okay, so we already have derived one equation that del x2 by del x1 equal to basically f2 by f2, x1 x2 by f1 x1 x2. Okay, so if you just rearrange it a bit and also simplify that it is just f2 by f1, then we can have f2 x1 minus f1 x2 equal to 0. Now if we integrate over that close along the closed curve L of a limit cycle, okay, then we have f1 dx2. Well, if you just take it to the other side, so this is what we have, f2 dx1. So if you now apply the Green's theorem or Stokes theorem on a closed surface, so what we have is f1 and dx2 minus f2 dx1 can be actually, this is for a closed curve, okay, so and you can have a double integration of the surface with the area, basically del f1 by del x1 plus del f2 by del x2 dx1 dx2 equal to, it should be equal to 0. So from here you can see that this parameter actually has to be 0. Only if it is 0, then actually we can have a limit cycle in the surface. But somehow if del f 1 by del x1 plus del f2 by del x2 is greater or lesser than 0, in that case it is not possible to have any limit cycle. So this is also one of the cancellation or nullifying type of theorem. So one of example 2.8 of this is from Slotin book. What a quick one. So x1 dot equal to gx2 plus 4x1 x2 square, then x over 2 equal to h x1 plus 4x1 x2 x1 square x2. Okay, so this is a simple function of x2, this is a simple function of x1, but what we need is basically del f1 by del x1. So this function with respect to x1, so this is x2, so it is vanishing, it's constant. So what is left is basically 4 4x2 square, and if you find del f2 by del x2, then what you're going to get, again this is constant, so what you're going to get is 4x1 square. So now if you add those two up, so del f1 by del x1 plus del f2 by del x2 equal to 4x1 square plus x2 square. So there is no way this can be 0, except that the fact is x1 x2 both 0. So this is not equal to 0. So, so that we can actually conclude that this system cannot have any limit cycle. Okay, so this is the end of your chapter 2. Assalamu alaikum everyone.